All right, so our last two examples of electromagnetic induction, changing electric or magnetic fields, creating the other type of field. First one we'll talk about is a magnet that moves through a loop of wire. So what I'm going to draw here is, I have one of these in my room. I won't show it too much, but this is an old style ammeter. Remember, an ammeter is something that measures current. It's got two leads here and here, and it's got this little arrow thingy. And basically what happens is if you pass a current through this, the needle will move to show you how much current is running through the ammeter. So let's say that we have a wire, okay? And I'm not going to put a power source in here or anything, but when I do the demonstration in a second, you'll see that I do have a power source in there. So I've just got a loop of wire, and let's say that I had a magnet. That goes through this loop of wire. And it has to actually be a loop of wire. Okay? What actually happens is that putting the magnet through the loop creates a changing magnetic field which induces an electric field. And the reason that any current happens is because there's an electric field inside the wire pushing the charges along, which induces an electric field which creates a current. Okay? So the simple act of putting this magnet through a loop in a wire will actually cause a current to happen. Now, I'm going to modify this very slightly with the circuit that I've set up. So I'm going to take you over to see this now and see that this actually does happen. You don't even need a source of voltage in order to have a current. So this is an old power source, okay? Here's a dial. Right now it's set all the way to 0, so there's no voltage coming out of this. This is a power source, though. It is plugged into the wall back there just so I have something. And the wires, let me show you. So we have wires. One of the wires runs here. There's an alligator clip, some clips there. And it runs into this red thing. And this red thing is a multimeter. This is a voltmeter, an ammeter, and everything all in one. Even an ohm meter. It can even measure resistance of things. Right now it's off. I can turn it on if I just hit this switch, but it's set to measure current. See where it says DCA? That's measuring the current. Now, so we have a power source, we have wires. We do still need something to use up that voltage or use up that energy. And that would be found right here. This right here is actually a resistor. You can see the little, I know that's really zoomed in, you can see the resistor part right there and the little metal arms. It's connected to these two alligator clips, and then this wire just simply goes back to the power source, creating a complete circuit. Okay? So, what happens if I turn on the ammeter? Okay? Is that there's basically no current in here right now. Okay, I've got this turned down as low as possible. Okay, if I turn up the voltage a little bit, and this is on a very low reading, so if I turn up the voltage a little bit, look, I turn up just a tiny bit, we can see that we're starting to get a current on there. So I'm going to set that back down to 0. Okay, this is as low as it can go. Now, there is another way with this staying at 0 for me to generate a current. I'm going to show you that, okay? All right, here's how I'm going to do it. I'm going to go back over here. You can see our paperclip still levitating nicely. We're going to de-levitate the paperclip by taking the horseshoe magnet, very heavy, over, and we're going to set it. Where are we going to put it? Let's put it right here for right now. Okay, so there's our horseshoe magnet. So, I said before that taking a magnet and putting it through a wire loop should cause a change in the current. Thankfully for us, we can do it the opposite way too. We can take the wire and move it through a magnetic field. So here's how we're going to do this. Okay. Gotta get these things close for us to see. If I take this wire, okay, you can see that if I move the wire around, I get a little bit of a jump because there is a magnetic field here. But if I take the wire and I move it through the magnet, where the magnetic field is strongest, I get crazy jumps. If I just hold it there, I really don't get anything. I have to move it through. Notice that if I move it this way, I don't get the crazy jumps that much. If I move it back and forth this way, I get something. I generate a huge current. Remember, this is reading the current anytime I move the wire through the magnetic field. Okay? And I promise I'm not doing anything with the power source here. Here, so you can see everything that I'm doing. Holding the camera with one hand, got the wire with the other, moving it through, not doing anything to the power source whatsoever. Okay? So the idea here, again, is that by moving charges through a magnetic field, you are putting a magnetic force on them. You're actually inducing a current, you're inducing an electric field. So it's very similar to what we just talked about on paper, taking a magnet and moving it through a loop of wire. Okay, I've always really liked that experiment. That's a neat little demonstration to show you what electromagnetic induction is. Move charges through a current, or move charges through a magnetic field, you will get a current in response. Very neat stuff. Let's talk about one more. This is this is one of my favorites. My other favorite, I should say. And that would be putting a magnet down a copper tube. Okay? So here's what we're going to do. Here's our copper tube. And our magnet is inside of it, falling down. Let's demonstrate this first. This is a good one to demonstrate. I'm going to get my little magnet, very, very strong neodymium magnet. Okay, it's very small, but you'll see that when I, here it is, right here. Very, very strong. Takes me a lot of effort to remove it. Okay, so very strong magnet, and we know that magnets are not attracted to copper. Okay, copper is not material that supports magnetic force. But copper is a metal, so it has lots of free electrons. So to show you what happens here, and again, this is not going to go great because I have, I'm trying to do all this one-handed because I got to hold the camera with one hand. What I have here is just a plastic pipe. Okay, I've got the magnet at the top, and if I drop it down the plastic pipe, exactly what you think is going to happen happens. Falls to the floor. Okay? So, copper pipe, no good. Nothing interesting, no magnetic effects. On the other hand, I showed you that this copper pipe is not magnetic. Okay? Doesn't stick. If I drop the magnet to the side of the copper pipe, again, because it doesn't stick, nothing will happen. Nothing. However, something interesting happens if I drop it right down the copper pipe. So, I'll do it and then I'll try and figure out a way for you to see this. Okay. So if I drop it down the copper pipe, listen. And then it comes out. It takes much, much longer to fall. And let me see if I can do this correctly. I'm going to try and drop it so that you can see it. Come on. Okay, that should be about good. Watch. Very, very cool. I'll show you one more time. Look look how much longer it takes that magnet to fall when it goes through the copper tube, as opposed to the side of the copper tube, or through the plastic tube. Here we go. Neat. Okay, let's talk about why that happens. So, let's talk just about, let's say, one little piece of that copper tubing. So let's say just like a ring of it right here, okay? That ring is that location is going to experience a changing magnetic field. Why? Because the magnet is falling. Makes sense. Okay, so magnet falling equals a changing magnetic field at that location. And since we know a changing magnetic field creates an electric field, that's the next step. You actually get an electric field created. Created an E field. Okay, so as the magnetic field changes at that, let's say, one location, like let's say, I don't know, like right here or so, that's going to create an electric field. And because the magnetic field is changing at such a rate that the rate of change isn't constant, that's also going to change. The electric field that gets created is going to change itself. So you get another magnetic field that gets created. Because what happens is, as this electric field, as this electric field gets created, what that's going to do is cause currents in your tube. And as it causes currents in the tube, that means little, electrons are going to move around. Since this is copper, it has lots of extra electrons. They're going to move around, and since they're moving, they're going to create their own magnetic field. Okay? So this created an electric field that changes. And this, in turn, creates a second changing magnetic field, but with one important characteristic. I don't need you to understand the math of why this happens, but the field that gets created is flipped compared to the first magnetic field. Okay? It has the opposite orientation. So what this does is it actually opposes the magnet. You can imagine if you drop the north end of the magnet down here, okay? So that this is the North Pole, this is the South Pole. The second magnetic field that gets created has the opposite orientation. Instead of north down here and south up here, it has north on top, south on the bottom. Think about what this is going to do. It's going to oppose the magnet because north and north will repel each other, all right? So the second changing magnetic field is opposed to the first one. So it repels it. It puts a force on it that's upward. Now, obviously, because the magnet still fell, the force of gravity is still greater. Okay? But what ends up happening is that you have this fall at a much, much reduced rate. Okay? The magnet doesn't drop as quickly because of this opposing magnetic field that was generated due to the electric field that was generated due to the original changing magnetic field. Magnet doesn't drop as quickly. There's a lot of neat videos of this on YouTube. You can find some really cool ones. Okay? This is just to kind of get you an idea of what electromagnetic induction can do. You can induce electric or magnetic fields simply by changing the other type of field, which usually means moving charges one way or another. Okay? And this has lots and lots of applications in motors and other electronics. It's very, very interesting. And for you guys, you don't really need to know a lot of the details other than recognizing when it happens and recognizing that it is a phenomenon we can describe. Okay? That's it for magnetism, and that's actually it for electricity. It's been a long unit. We're going to move on to waves next. I like waves as a unit. It's pretty fun. Can't wait to talk to you guys about that stuff. See you later.